Welcome back to the Explainer. Let's go ahead and initiate our telemetry interface and get those systems booted up. Today, we are going to explore the absolute bedrock of physics, and that is one-dimensional motion. We're going to strip away all the messy complexities of our 3D world just for a bit so we can totally master the fundamental rules of how things move along a single, straight line.
Okay, let's dive into this. Have you ever actually stopped to wonder how NASCAR engineers tune their cars to absolute perfection before a big race? Or, on the flip side, how geologists track the incredibly slow, grinding movement of tectonic plates to predict earthquakes? I mean, on the surface, it seems like entirely different science, right? But it's really not. They rely on the exact same principles of straight-line kinematics. By understanding the rules of moving in a straight line, we can literally predict the behavior of almost anything in the universe.
So, here is our flight plan to mastery today. We're going to start with initialization, position and displacement, then rates of change, followed by the second derivative, acceleration. Fourth, we'll open up our toolkit for constant acceleration, and finally, we'll wrap up with applications in free fall and gravity.
All right, kicking things off with Section 1, initialization, position, and displacement.
Now, what's really interesting about this is how we have to redefine the words we use every single day. To establish our basic telemetry grid, I want you to imagine a straight line stretching infinitely in both directions, with a 0 point right in the middle. We obviously need to know exactly where an object is before we can figure out where it's going, right? Well, notice how we're contrasting two concepts here, distance and displacement. Distance is a scalar. That just means it's the total meters moved, regardless of direction. Displacement, however, is a vector. It cares deeply about direction and gives us the exact net change between the initial and final position. Think about it like this. See you're driving a beat-up pickup truck for 8.4 kilometers before it just totally breaks down. You then get out and walk another 2.0 kilometers in the exact same direction to reach a gas station. Your distance is 10.4 kilometers. And because you moved in a straight line in the positive direction, your displacement is also positive 10.4 kilometers. But, and here is the kicker, if you gave up and walked back home instead, your distance would actually increase while your displacement would drop all the way back to 0.
Moving right along to Section 2, rates of change, velocity versus speed.
Okay, so we've plotted a position, but the universe is rarely just standing still. We need to determine exactly how fast that position is changing over a specific time interval. And just like distance and displacement, speed and velocity are fundamentally different beasts. Average speed is your total distance divided by your time interval. Average velocity, though, is your net displacement divided by the time interval. Because it uses displacement, velocity is a vector. It includes a direction. And let me tell you, that direction is absolutely crucial for our readouts. You wouldn't want air traffic control to just know a 747 speed. They desperately need its velocity so they know if the plane is flying toward the runway or away from it.
But average velocity only tells us the broad story of a trip. What if we want to know how fast you're moving right at this exact second? For that, we use instantaneous velocity. To find this, we take that average velocity equation and we sort of zoom in to an infinitely small time interval. In calculus terms, we take the limit as the time interval approaches 0. This gives us the exact speed and direction at a specific given instant. Mathematically speaking, it's the first derivative of position with respect to time, which we write as v equals dx over dt.
Up next is Section 3, the second derivative, acceleration.
So position changes over time, and that gives us velocity. But what happens when the velocity itself isn't steady? Well, acceleration is defined as any change in a particle's velocity over time. Now, in everyday conversation, we usually use the word acceleration to just mean speeding up. But in physics, it's so much more than that. Because velocity includes direction, any change in direction is also an acceleration. Think of riding in an elevator cab. When the cab starts moving up, it accelerates. When it hits its cruising speed and moves at a steady, constant rate between floors, its acceleration drops entirely to 0, even though it's moving fast. And then, when it finally slows down to stop at your floor, it's experiencing negative acceleration. Slowing down, speeding up, or reversing direction, they are all governed by this one single concept.
And this brilliantly illustrates the mathematical descent that builds the entire foundation of kinematics. Look at how each level derives directly from the one right above it. It's like a mathematical waterfall. You start with position, x. You take the first derivative with respect to time, dx over dt, and boom, you get velocity. You take the derivative of the velocity, dv over dt, which is exactly the same as the second derivative of position, d squared x over dt squared, and you arrive at acceleration.
It is this beautifully unified system where just knowing the formula for position allows you to mathematically unpack the entire motion profile of an object.
Let's look at Section 4, the toolkit, constant acceleration.
In the real world, we frequently run into scenarios where acceleration remains perfectly steady. Think of a car hitting the gas at a green light, or a freight train applying its brakes. For these situations, behold your master decoder ring, the big 5 equations of constant acceleration. Now, I know memorizing equations can be a bit dry, so instead I want you to focus on the missing quantity column. Any standard constant acceleration problem is going to give you 3 known variables and ask you to solve for a 4th. That means out of our 5 core variables, displacement, final velocity, time, acceleration, and initial velocity, one is always completely missing from the problem. By simply identifying that one missing variable, you can instantly select the exact right equation to predict the motion. It's literally a foolproof toolkit.
Let's move to Section 5 and see how this builds: real-world application, free fall, and gravity.
Now let's take our newly unlocked one-dimensional toolkit and turn our horizontal x-axis vertically into a y-axis. We're going to substitute our acceleration variable a with a negative g. And what exactly is g? It is 9.8 meters per second squared. This is Earth's universal freefall acceleration rate. If we neglect the messy effects of air resistance for a moment, every single object, regardless of how heavy it is, accelerates downward toward the center of the Earth at this exact constant rate. To really hammer this home, look at this incredible stroboscopic capture. We have a feather and an apple free-falling side by side inside a vacuum. This is absolute visual proof that mass does not matter in freefall. Notice how the distance between the objects in each flash increases identically as they fall. That visual stretch represents their speed increasing at the exact same rate. They are completely, undeniably locked to that constant 9.8 meters per second squared acceleration. Whether it's a tiny, wispy feather or a dense, heavy apple, gravity pulls on their velocities equally.
So, the crucial takeaway for today is this: one-dimensional kinematics, really understanding displacement, velocity, and acceleration along a straight line, is the foundation of all physical motion analysis. But as we know, our world isn't just a straight line. If we've mastered predicting motion along a single axis, what happens when a baseball is thrown or a rocket launches, arcing dynamically through the sky? How do these exact same big 5 equations adapt when a projectile breaks free into 2 dimensions? Keep that in the back of your mind, because that is exactly where our telemetry is going to take us next time. Thanks for focusing in with me today, and as always, keep questioning the mechanics of the world around you.